All right, what's 1? The new thing we learned yesterday. The definition of the derivative, right? Okay. What else? Zooming. Meaning what? Graph it. So 1 is the original point. Pick another point really close. 1.001. Plug that in. Do a slope calculation. Okay, what's another one? Estimate slope. What do you mean?
Just like on the graph.
Like do a graph, put it on your paper, put a tangent line in there, do rise over run. Right? Estimate the slope that way. Okay? Any others?
Derivative function on our graph.
I was just going to say, I showed you one yesterday, right, with the calculator. Menu, calculus, dy over dx, right? The cheating kind of way, which, you know, it's fine. Yeah, it's fine if you do it. It's probably not anything you're going to need to do. A lot of times will be no calculator situation. And even when you have your calculator, when you see what we learned today, you'll find out that there's faster ways to do it without the calculator than to actually graph it and have to go to that menu option and do it. But it is one way you can do it. Okay, so that's probably about it. Those four maybe. You know, if we count the calculator one as an option, sure. Okay, so that's what we have. Now we'll see if we might add to that list a little bit here today. All right. So the first one you mentioned, the limit definition, the long way of doing it. We did a couple of those yesterday. You know, here was an example of one right here. Here was another example of one right here. Using this definition in red over here as our guide. Now remember, you know, we need to memorize this. You know, this would be a good question on a quiz. Describe why this definition gives f prime of a. What about this, what characteristics of this give the slope at point A? Well, it's this stuff right here. There's two pieces to this. What's this piece? That's just slope. That's just y2 minus y1. x2 minus x1. That's all this is rise over run. This piece right here is called the difference quotient. In your book, they reference that in your homework today. Subtract the y, subtract the x. It's the difference quotient. That's all that is, slope between 2 points. And then what's this do?
Makes the 2 points become
2
one.
points become 1, right? H is the distance between the 2 points. That's all H is, right? We got this point and we got another point H units away. If we let that distance go to 0, the 2 points become 1 and we find the slope of the tangent line. Because don't forget, that's what f prime of A is. F prime of A is the slope of the tangent line. So if we let the 2 points become 1, it turns into the tangent line and that gives us a slope of the tangent line. Because this gives a slope, this makes the secant line turn into the tangent line, and there you go. So being able to describe that and understand why this is the slope, why this is f prime of A right here, that's, you know, we need to understand why that is. All right, so we move on here with a couple of things, and I've got a couple in the problems in the homework that I want to go through. Now, I don't know, I'm going to run through several things. You can jot some of this down. It may end up being just kind of a jumbled mess when you write it down. But I just want to go through a couple of things here, some alternate notation that is not really a huge deal like this one isn't. Now, there's some other notation that we'll see more today that is kind of a big deal. So the more you see it, the bigger deal it is, I guess, right? The bigger, more important it is. This is just another way of doing the derivative. I think you might have a homework problem or two that's like this. Maybe one of them today was even like it. I think maybe, I actually think did we do 31? We didn't do 31, did we? No, we didn't do 31, but I think there might be one in tomorrow's homework that's like that. Maybe not. It is not a huge deal, but it does show up sometimes in the AP test, kind of out of nowhere. But you know, the AP test has some questions like that. That's how come a 60% gets you a 5 usually, right? I mean, when 60 or 65% gets you a 5, which is the highest score you can get on the AP test, you know there's some pretty hard problems on there. Some problems that you just maybe don't see, right? I mean, that's true. That's about what it takes to get a 5. This is about a 65%, okay? So in our class, that's a D, right? I mean, so there's a scale built into that test. So sometimes there are some problems on the AP test that we just couldn't possibly remember or really study all the different little things. We'll talk about them, we'll have them from time to time. If they don't show up very much, sometimes there'll be one you say, well, that's one I might not get. You know, I mean, we just have to do that sometimes. But here's the notation. So how's this different? Well, if you think about how we did the notation yesterday, we said here's point A, and we'll make a second point A plus H. And we'll let that second point get closer and closer. In other words, let H approach 0, and then it becomes the tangent line. And so here's our two Y values, f of A plus H and f of A, right? And so that's what we did. And that's how we looked at it. And that was our notation here in the red. This thing right here was the notation we used. Well, another way you could do that is label the first point A, and there's your Y value f of A, and label the second point X, and label its Y value f of X, and then say as X approaches A. So this is just another way of doing it. This part is still sloped between 2 points. One is A, one is X. And this says let the X approach A. So let this slide towards this, and those 2 points become 1. So it's the same thing. It's the same thing. Now, this isn't as useful, to be honest with you, which is why we don't use it very much. All this will let you do is the slope at a point. It'll only let you do the slope at 1 or at 3 or at 4, which is what we've done so far. We're going to learn today that we want to do the slope at all points X. Not just at 3 or 1, but we'd like to do f prime of X. Not just f prime of 1, f prime of 2, f prime of 3. This formula can't do that for us, but the one we learned yesterday can. So we're going to do that. All right. Here's another alternate notation for derivative that we want to get used to. Now this one's a little more important, and so I'll point out a couple of things here. So far we've been using this over here. So if I have a function f is sine x, then the derivative we know is cosine x. That's one we learned already, right? We found out that was kind of cool. That all the y values of cosine are the slopes of the sine graph. Okay? So that was kind of interesting. Well, that's how you would write that as a formula. Now, sometimes we don't use f notation. Sometimes we just use y. So we say y equals sine x. Then we could write y prime would be cosine x. Or we've got this new notation that we saw in our calculators yesterday. Right? That dy over dx. Now, that's called Leibniz notation. Leibniz. Gottfried Wilhelm von Leibniz. If you're math people might remember him. German guy. He is one of the co-inventors of calculus. Now we say inventors. He along with Isaac Newton developed a lot of the concepts that later became calculus. Okay? They didn't know they were just inventing something out of thin air, but what they did is they were working on these ideas kind of separately, and then as years went by, these things started to connect and tie together, and that's what made it a big deal, the fact that there were these connections. We already talked about a little bit that slope of a line is connected to area. We did that with those explorations the first couple days. Who knew? But eventually, people figured out that, hey, there's kind of some connections here that has far-reaching implications for a lot of other things. And that's what made it a big deal, and that became the ideas of calculus. But Leibniz, this is kind of the notation he used for rate of change. And it just comes from this. It just comes from delta y over delta x, change in y and change in x, which is slope. So that's where the dy dx notation comes from. Now, second derivative notation, we've been doing the double prime, but Leibniz did this kind of notation with the 2's there. Now, those don't mean squared. They look like squared, but they're not squared. Those just mean second derivative. The 2 just means second derivative. Okay? So if we ever see that on problems, that's all it means is second derivative. Okay? All right, now here's the coolest notation of all, and we're going to use that a lot today right here, is this notation. Because what this allows us to do, this kind of uses Leibniz notation, it allows us to do the rule of the derivative in one step. Instead of having to write f and f prime, we just write this. And basically, here's what we do. We take our Leibniz notation with the y here, and we take the y out. Since y is sine, we just take the y out and replace it with the function. So here's how you want to read this. The derivative of sine x, and then the bottom part we just say with respect to x. In other words, that's our input variable. X is our input variable. So this bottom thing doesn't really do anything. It just kind of tells us, hey, x is our input variable. Kind of like here, f prime of x. This x doesn't really do anything. The f prime tells us it's a derivative. The x is just saying, hey, x is your input variable. Same thing here. dy dx means a derivative of y, and then this part just means with respect to x. Okay, so we're not really dividing anything here, it's just notation. Okay, so what this is saying is the derivative of sine x is cosine x, so we can put that all in one line. Matter of fact, we have another one, we could even start a list here. So, right, I don't know that you want to start this list right now, but we will eventually write out a list of these, all these things we're coming up with. So we know that one. What's the other one we know? What's the other derivative we know? E to the x. The derivative of e to the x is e to the x. Do we know any other one? I'm not sure we do we? I think that's all we do. But you can see we'll eventually we'll have a big old page full of derivative rules of these things. A lot of them will be pretty easy. A few will have to work out to memorize a little bit, but most of them will come pretty natural. Okay, we're going to add to that list a little bit today, actually. All right. So, just some notation things as it crops up. All right. All right. Some algebra stuff. We'll get to that in a minute. Okay, let's look at number 34 on our homework today. 34 and 35. It's kind of funny. I had I had a few people come in and get help this morning, a few people at lunch. Hardly anybody asked about 34 and 35. And I thought those were kind of tricky. So I don't know what that means. Were they easy? Or maybe you thought they were easy, but it was asking something different than you thought. Maybe that's what's going on. Okay? So we're going to actually do some more of this. Some more things like this. This is kind of a big deal. Actually, what this is the long way in reverse. This is the long way in reverse, these problems. Because here's what we learned yesterday, that here's the formula for derivative. Looks like this. And so what we did yesterday is we said, think about what we did. We said, okay, I'm going to start with an f function. And I'm going to tell you I want the slope at 2. So they told you the function and they gave you a. Right? They told you f, the f function, and they gave you a. And then you had to plug it into the limit thing. It ended up looking like this. We worked it out and we found it. Well, now we're doing the reverse. They're giving us this limit, and they want us to tell them what the original function was and what was the a value. Okay? So we're just doing this in reverse. So if we go to this, we got to look at this and say, does this look the same? It kind of does. This is our h, right? Obviously, this is in the place where the h is. So what's the a got to be? Is the a 9 or 3? I think it's got to be the 9, doesn't it? Now here's how I would do this. Here's where I would focus in. I would focus on this part right here. The first part of that limit has a plus h plugged in where the x was, right? Remember peanut? Peanut goes in for the x, a plus h goes in for the x. So a plus h goes in where the x must have been in the function. So first of all, when I see 9 plus h, that tells me the a is the 9. So that means that this must be that. Correct? This limit here is f prime of 9 for some function f. Now my other job here is to figure out what the function is. What do you guys think? Square root of f. Okay, well maybe you guys did think this was easy. That's right. Now, why is that? Because peanut goes in where the x was. A plus h goes in where the x was. Well, where did 9 plus h go? 9 plus h went right in there. So wherever the 9 plus h is, that must be where the x was. So this was square root of x. Now, the other thing that fits, some of you are wondering about that 3, if a is 9 and the function is square root of x, what's f of 9? Square root of 9, right? It would have been easier if they would have wrote square root of 9 then, instead of the 3. It would have been less confusing. Okay? But square root of 9 is 3. So sure enough, this does look like that for this function and this a value. Now the other thing they want you to do is estimate what that is. Well, here's where you get on a calculator. You graph this function. By the way, for our next quiz, for this chapter, we probably need to get to the point where we know that the square root of x graph is an the sideways parabola. It's the top half of the sideways parabola. Okay, this is a square root of x function. 9, be out here somewhere. So you can just graph that. Do like we were just talking about. Pick 2 points, right? Pick 2 points close to 9, 9 and 9.01. Plug them in, do a slope calculation. You just said estimate the slope. So just do that. Graph the square root function, pick the point 9, another point close, do a slope calculation, and that'd be what they wanted you to do. Okay? They did not want you to go through the whole long way on this. Okay? Now, we'll talk here in a minute about what we would do if we were going to go the long way on this one. But they didn't want you to do that. All right, let's go to 35. Does this one look like the definition of the derivative? Does this one look like this? Well, I see the h there, so that looks like it. A plus h. I don't see an a plus h here. Or do we? How about if that's at 0 plus h? Couldn't a be 0? Sure it could. And if a was 0 there, then a would also have to be 0 here. Right? So it looks like the a is 0. And it looks like the function that I must have started with was what? Well, remember, the a plus h got plugged in where the x was. So what was my function? Cosine x. My function must have been cosine x. That means this must have been cosine a, which would be cosine, what's cosine 0? Oh, 1. Okay, so it does match. Now, it would have been easier if they would have wrote it that way. If they would have wrote this cosine 0 plus h minus cosine 0 all over h, then it would have looked a lot more like this. But they went ahead and simplified it a little bit, and so then it didn't look like it as much, so we kind of had to deconstruct that a little bit. Okay? All right. So, and you wouldn't work that out the long way with cosine. That would be hard to do anyway. Algebra would not work, really. Algebra techniques would not really work on that, like we might want them to. Okay, we're going to work through a problem here. I'm going to show you some algebra stuff here in a second that we're going to need for 44. I want to talk about 44. And I want to make one comment about 43. On 43, you had to do 4 plus h cubed. We're going to have to do this here in a minute or something similar to this. One way to do 4 plus h cubed is to simply write it out. This is probably the way most of you would pick, and I would say that's a good idea. And then you just have to FOIL that, right? So you FOIL that like so. And then you have to do what with this? Just distribute, basically, right? You got to take everything in this one. You have to take 4 times each of those, and you have to take h times each of those, right? You just got to write it all out, combine your like terms, and away you go. And then things will happen. So it's not a lot of fun, but that's how you would do that on 43. Okay, we're going to do a cubed one here in a little bit, so that's going to be similar. Okay, so we're going to practice that one more time. Okay? All right. Before we do 44, there's an algebra technique you need to know on 44, and there's another algebra technique that we would actually use if we were going to do this, if we were supposed to do 34 the long way. Problem with 34 is we can't FOIL anything. It's got that square root in it. Now, when I talk about 34, I'm talking about, now back to this part right here. Okay? If we were going to work this out the long way, what algebra could we possibly do to that to make that h cancel? Delta x cancel. So I'm going to show you these two algebra things right here. Now, I don't know that you need to write these down or copy this down. I think it might be best just follow through with it right now. We will be, over the next couple days, we'll be doing some worksheets and some practice on this algebra. Okay? So I don't think it's worth probably writing down right now. Let's talk about the top one, conjugate. I was talking to Miss Andreessen here earlier. She said she knows you guys worked on some of this for sure there. And with trig identities last year, you might have done some of this. But on this top one, if you want to get rid of this radical here in the bottom, you can multiply by this, which is called the conjugate. Okay, what that does is it allows, when you FOIL that, square root of x times square root of x is x. The outers and the inners disappear. That's why you do a plus b, a minus b. That's what the conjugate is. And then the last times the last. And so now you end up with a radical on top, but that was the whole point, was to get rid of it. That's a little different than what we're going to do. What we want to do is get those H's to kids. But this technique will make that happen. So multiplying by a conjugate. When we do our next quiz, there'll be 3 algebra things you're going to have to do. One is the FOIL and cancel stuff we were doing yesterday. One is be able to do a conjugate multiplication. And then the last one is the common denominator thing. Now, one way to do it is common denominator. I think my favorite way is not really common denominator. It's more what I call clear the fractions. Now, Mrs. Payne calls it bow tie. You guys do that with her on some of those trig identities, a bow tie thing. So I don't care how you do it. I've shown you 2 different ways up here. But when you have a fraction in a fraction, that's what happened to you on 44. You get a fraction in a fraction. How do you get rid of that? Well, one way is the old bow tie. Now, I showed it a little different here. Bow tie is basically getting a common denominator. Okay, so I decided my common denominator would be xy. So I took this top and bottom times y over y, took this times x, top and bottom. So I'd get 3y over xy and 2x over xy like this. Now I got a common denominator, I can put them together. Now you guys recognize that as a bow tie. If I just take that times that, right? There's my 2x. If I take that times that, there's my 3y all over the xy. Okay? So if you want to do it that way, that's fine. You kind of skip this step and you end up here. Then you got to multiply by the reciprocal to get that x squared out of the bottom. Invert and multiply. So I invert and multiply, and so I multiply across here, xy times x squared, I get that. Okay? So you can bow tie, invert and multiply, and do that. What I think is a little cleaner method is to take that common denominator and just make that your well-chosen one. Right? Well-chosen one. In other words, here we multiplied by y over y, x over x, those are just 1. Here I'm going to multiply by xy over xy, which is just a 1. Now look what happens. When I multiply that times that, what happens? The x cancels the x, and I end up with just 3y. When I multiply this times this, the y's cancel, and I end up with just 2x. And then down here on the bottom, I multiply by xy, and I just get that. So in one fell swoop, I end up with that answer, just clearing out the fraction. So you got fraction and fraction. You just look at the denominator, get the common denominator between them, and multiply that times your top and bottom. And that will make nice things happen. That will get these denominators to clear out and clear the fractions. Okay? So one of those 2 techniques you need to be able to do. So let's go through number 44 because that involves that. Oh, you can see how 34 here would involve the conjugate, by the way. Here's the top has a radical minus 3. So what I would do, and you'll get a chance to practice this later on. What I would do here is multiply this times radical plus 3. I had radical minus 3. I'm going to multiply top and bottom times radical plus 3. And good things will happen when I do that. Now, you didn't have to do that on 34, but that's just so you see where you might use that conjugate idea. Okay? All right. So here's 44. So I've got it started. You're going to get one of your homework problems will be another, be similar to this, and you'll get a kind of practice this common denominator thing again. So, okay, so see I've copied down the formula, derivative formula, put a 4 in for a, because we're doing f prime of 4. All right, so now what? F of 4 plus h, what do? Put 4 plus h in for x. So that gives me 2 over 4 plus h. Right? And then f of 4 would be 1/2. Right? And then that's all over h. And look what I got. I got a fraction inside of a fraction. So if we choose the method that I was talking about, we would get our common denominator here, which would be 2 times this. And I would just multiply that times the top, and I would multiply that times the bottom. That is a quick way of doing it. Now, if you want a bow tie, you can bow tie there, that'll be fine. And then you'll have to invert and multiply the h on the bottom to get that out. Okay, or so you don't have a fraction. But if you want a bow tie, go for it. I kind of like this. So think about what happens here. So we're going to take that times each of those. Let me recopy here. So when I take this times this first one, what happens? The 4 plus h is canceled. And I have what? 4. Then I take this times this. The 2's cancel. So I have minus. Now you got to be careful here. I got to put parentheses around that 4 plus h. That's why I did not distribute that 2 through here, right? If I don't distribute the 2 through there, then it's easier for me to see the stuff that cancels. Okay? So the top, so right there, by multiplying by that, and again, all I've done is multiply by a 1, a well-chosen 1. So I got that. Now the bottom, I don't even care about right now. I'm just going to write it down. I'm not going to distribute. I'm not going to simplify anything because I'm hoping stuff cancels. So I want to leave that alone. It's all multiplied out in factors, so that'll be good. I want to leave that like that. What happens on top? What happens on top? 4's cancel, I'm left with what? Careful. Negative 8. See, that's the problem when people don't put the parentheses. You'll end up with h there, and you'll have a wrong sign on your final answer. 4 minus h. You got to distribute that negative through there. Okay? What about down here? We got h times 2 times 4 plus h. I'm just going to keep writing that down. I'm not going to mess with it. Because now what do you see? H is canceled. All right? Which again, we learned yesterday is what we want to happen. Because now, don't get lost in the forest here, right? What's that saying? You not be able to see the forest for the trees, right? Which means you get in the middle of the forest and you get so focused on all these trees that you can't see the whole big picture, right? That's what that means. And that's what happens to you here. You get so caught up in all the algebra, which is important. You got to do it. But you forget what we were doing. We were taking this function and trying to find the slope at 4. That's what we're trying to do. And we're trying to let the 2 points become 1. We know the 2 points can't actually become 1 or the formula falls apart. But what we do is we can see that as h gets close to 0, right here, when those cancel out, now we can plug a 0 in for h because something nice is going to happen. So let's keep going. Let's keep going with it. So we get limit h approaches 0. Now we got negative 1 over 2 times 4 plus h. Right? Well, what's that equal? Why can we plug a 0 in for h? Well, because when the points get really close, when h gets really close to 0, this 4 plus h basically becomes 4. It's getting closer and closer and closer to being 4. Okay? So if the 2 points ever could become 1, we know this would turn into a 4. And we get negative 1/8 as our answer. So we know that if the 2 points ever could become 1, we would get our tangent line. And if the 2 points could become 1, h would become 0, and this slope would be negative 1/8, and that's the slope of the tangent line. And to verify that, you could go to your calculator, but this is another graph we ought to know. The graph of 1 over x, or we ought to begin to know as we see it more and more. This is the graph of 1 over x. How would the graph of 2 over x relate to the graph of 1 over x? Huh? How would 2 over x compare to 1 over x? It's a vertical stretch of 2, because all that is taking 2 times 1 over x. It's just a 2 multiplied on the outside, is all it is. It's a vertical stretch. Well, what's that going to do? It's just going to make this go up a little steeper, this go down a little steeper. It'll basically look the same. I mean, it'll be very similar. So this is just a vertical stretch of a basic 1 over x hyperbola. Now, out here at 4, what did we get the slope to be? Negative 1/8. Reasonable? Seems pretty reasonable. Up there, it's getting pretty flat, but it's still going down. So if we had 1/8, we definitely would, right? If we had forgot to distribute that negative, and we had 1/8 as our answer, we could definitely see that can't be true. It's got to be negative slopes there the whole time. Okay? So negative 1/8 seems like that's reasonable. All right, so we need to be able to do this algebra here. All right? All right, so those are a couple of them that I wanted to go over. A lot of the other homework was just slope between 2 points, stuff like that. If you had some issues with some of that, come in and see me. If you had issues on a bunch of them, then that's definitely means you might want to come in and we can spend some time on some of that. But these are the ones I really wanted to go over because I think those had a lot going on and were kind of tricky. All right. Let's see. I want to add to that list. Okay. Got our notation down. All right. Next thing we want to do is, okay, let's go here. This you might want to write down. We're going to go to another, or we're going to look at another notation for this slope. It's going to be an offshoot of the one we learned yesterday. I was saying earlier that, this is pretty important. Everybody stand up. We better take a 60-second stretch break. Okay? Yeah, I should have done it yesterday, right?
Okay, everyone stand up.
Take a little look. Oh, that's funny.
It's my favorite thing that he
Unwind.
does. Lefty
Who
Lucy,
says
righty
that?
tighty. Mr. Klein. He'll have us stand up and we'll all have our instruments like in our hands. He'll be like, now turn around. He's really funny. Yeah, that's why I sat next to him. That's why I sat next to him in poli-sci and if he's really
All right, time's up.
What?
60 seconds. I timed it.
Enough time. I didn't have enough time to do Happy Jacks.
What's that?
We did like what's a happy? Who doesn't know what Happy Jacks are? Want to demonstrate? Come on,
Jumping
Brenna,
jack?
let's do
Also
Happy
jumping
Jacks.
jack?
I'm not doing this alone. Doesn't do Happy Jack. Callum. Do some Happy Jacks.
All right. Okay, so earlier I was saying that this formula gives us a slope at point A. So this gives us f prime of 1, f prime of 3, f prime of negative 1, whatever. What we would like to do is get slope at every point. Matter of fact, we've kind of done that already with our sine and cosine thing. I mean, that's what this right here says. Okay, this says that the derivative of the sine function at all points is cosine. So all we need to know, if we want to know the derivative at 2, we just plug in a 2. Cosine of 2 is the slope of the sine graph at 2. Right? So f prime of x is all of the slopes. So we know that from graphs, right? If you graph f prime of x, all those y values are the slopes of the f graph. So what we would like is an equation, all right, for different ones. So how can we do that? Well, all we have to do here is tweak this formula a little bit. Instead of a as our input, we'll do x as our input. Now we can't do that on that other form I gave you because it's already got x in it. It has to have a in it, but this one doesn't. So we're going to make x be our point instead of a. I mean, it's really that easy. A stands for some individual point. X is going to stand for all the possible points. So we'll make our second point be f of x plus h, our second y value. Here's this slope, and we'll let h approach 0. And so we subtract the y's, we subtract the x's, and our derivative now looks like that. It's the same thing, but we take out the a's, put in the x's. It's the same thing. I mean, there's nothing really new about it other than it now represents all x values. So when you see me write the definition of a derivative, probably most of the time from now on, we'll do it with x instead of a. And there'll still be some problems where you'll see it with an a. But this is just more multi-purpose because what we can do with this is if I want to find f prime of 1, I can. I'll just put a 1 in for x. If I want to find f prime of 2, I'll put a 2 in for x. But if I want to find just f prime of x, I'll leave an x in for x. Right? And that's what we want to do next here. I want to find a formula for the derivative of that function right there. I don't want f prime of 2. I don't want f prime of 1. I want f prime of x. So we are going to do it. We're going to do the limit as h approaches 0 of our new version. We're going to write it out in f notation first. just like you should have on today's homework. And we're going to go through this the long way. We're going to go through it by that definition, using that function, and hope at the end it should give us the slope at all points x. Because it certainly worked to find the slope at 1 or the slope at 2. It gave us the slope at those points. So it should work for x. So tell me what the next thing I would write down would be. So the next thing I would do is substitute x plus h into there. And that would be x plus h squared. And then I would substitute, x in for x. And that would be x squared. And then all over h. Oh, I forgot my limit. I did get lazy. Yes, I did. Okay. So, this is the algebra we worked on yesterday. We got x plus h quantity squared would be what? X squared plus 2xh plus h squared minus x squared all over h. X squareds cancel out just like things canceled out before. We can factor out an h. Which allows us to cancel an h. And what does that mean? The derivative of x squared is 2x. As h approaches 0, if the 2 points could become 1, the slope is 2x plus whatever h is. As h gets closer to 0, that gets closer to 2x. If the 2 points ever could become 1, h would be 0. The slope would be 2x. So the slope of any tangent line is 2x. So what we just learned is the derivative of x squared in our new notation. We just learned that right there. We just learned the derivative of x squared is 2x, right? Because we let h be 0, and that actually worked out pretty nice. And that might be surprising to you. Maybe some of you saw that coming. I've had a few of you ask me about some of the graphs we've been doing. You've noticed a pattern maybe in some of the f and f prime. Maybe we did the matching. Or some of you were asking me about noticing some patterns with some of them. See if that is holding true here today. Let me give you another one, and I'm going to let you do this one. I told you I'd let you practice the x cubed a little more. We had an x cubed on number 43, but we were plugging in f prime of 4. This time, let's do just f prime of x. Now, I'll go ahead and write the first part of it for you, which is just the formula. I always like to write the f notation down. I know you don't have to. Many of you probably could get right into just plugging your x plus h in for x right away. Make that be your first step. As the functions get more complex, I think it's easier to get confused, so I always like to write that step down. Okay, so you guys, we already talked about how to do a cube, so go ahead and do that. Finish it out and see what you get. Now, before you get done, though, you might think about a prediction here. What do you think is going to happen? Write it down at the top of your page or something. You know, what do you think the answer is going to be? All right, some of you are getting done, some of you are still going, so that's fine, keep going. You know, I'll make a comment about algebra on, you know, the algebra stuff. I mean, the hardest part of this is the cubing it out, foiling and then distributing everything, combine like terms, you make a mistake in there. You know, this is an algebra class, and I'm not, you know, I certainly don't want you to lose tons of points because of algebra. I want to be able to still get across the calculus concepts, but you gotta understand that when you go to college, and more times than not, you get a professor in college who will say no calculators of any kind, and they want everything by hand and algebra. You run into that stuff. And it does make it easier. If you can whip out the algebra pretty quickly without much problem, it does make it easier because you don't get bogged down. Okay? But, you know, there's some algebra I'm going to show you that I want you to be able to do on some quizzes, but I'll try not to make it so awful that the algebra just causes you to really go to lose a bunch of points. Now, I will tell you this. Here's what I got when I foiled that out. The cubic. Now, up on the board over here, I've put Pascal's triangle. Did you guys talk about this at all last year? Remember seeing this before?
Mm-hmm.
Okay, some classes might have, some did. It's kind of cool. It's got a lot of different hidden features in it, things that are in there. 1 and 1 makes the 2, 1 and 2 makes the 3, and so forth. 1's down on every side, and you can just keep going forever. One of the cool uses of this, Pascal's triangle, is binomial expansion. When you're expanding a binomial like this, each row starting with 0, if n is 0, if you did x plus y to the 0 power, that of course is 1. If you did x plus y to the first power, you'd have 1x plus 1y. So these numbers are the coefficients of the answer. If you did to the second power, this would be 1x squared plus 2xy plus 1y squared. And so the one we're trying to do is cubic, so that's how I did it. You could do a little shortcut here for cubing a binomial. This would be 1x cubed plus 3, and then the pattern is that the first thing's power starts at 3 and goes down, and the other power starts at 0 and goes up. So you have 1x cubed plus 3x squared h plus 3xh squared plus 1h cubed. And that would help you with a 4th degree, 5th degree, because those would really get messy. So Pascal's triangle could be really helpful for those. We're not going to, it's probably not worth memorizing. I'm not going to make you do a whole bunch of 5th degree powers or anything like that. Okay? But that is something that could be used here. Okay? So, we go through here, and sure enough, the x cubes drop out, like they did before. And we end up at this, where, lo and behold, we can factor out an h. So when we factor out the h, of course, it will cancel, which is what we wanted to have happen. And now we can put a 0 in for h, which makes those two go away. Did anybody predict that? A few people did. Anybody think it was going to be 3x? Yeah, their class, that was a popular choice. People thought it was going to be 3x. So the derivative of x cubed is 3x squared. So we won't do it, but if we were to do x to the 4th and go through the whole long way, what do you suppose would come out at the end? 4x cubed. And that's kind of cool. I mean, we shouldn't just skip over that. This is pretty powerful stuff. Think about where that came from. That came from slope. That simple little pattern of what does it look like? The pattern is bring the 4 down in front and drop the power by 1. I mean, that's what this last one seemed to do too. Bring the 2 down in front, drop the power by 1. So that would be x to the 1st. That came from slope and FOIL and Pascal's triangle and canceling. And there it came out in the end. And that will work with any power type function. So what we have just learned is another rule that we could put into a list. This one you actually might want to write down. This is going to be a big part of your homework today. That anytime you have x raised to a numeric power, anytime you have a function with x raised to a numeric power, the derivative is that power brought down in front, and then the new power is 1 less. That is called the power rule for derivatives. The power rule for derivatives, and it's written in your book that way. Okay, so we talked about the power rule. Now that's x raised to a power. Now some people confuse that with e to the x. You know, all of a sudden we learn that power rule, and now people want to, when they do the derivative of the x, they want to bring the x down in front and write x minus 1. No, that's different. This is x raised to a numeric power. This is a number raised to an x. Those are two different types of functions. These are called power functions. These are called exponential functions. So it's a whole different deal. Okay, so it's a whole different rule. All right. Now, so that's a shortcut. That's a really nice shortcut. So we talk about the long way of doing these now. Think about what we could have done back here. Think about what we could have done with this one. What's another way to write 2 over x? 2 times x to the negative 1. Would the power rule apply here? Does this have x raised to a power? Yes, it does. Now it's got a 2 sitting out in front. What do we do with that? Well, we're going to talk about that in a minute. For right now, we're just going to leave it there. Turns out that's what you do it. Okay? So what do you suppose the derivative of this would be then, according to the power rule? We're going to practice some of these here in a minute. We bring the negative 1 down. So that'd be negative 2, x to the... You got to decrease it by 1, right? So it was negative 1, so we take away 1. It's now negative 2. Now let's look at that. I could write that as this right here, correct? That's my f. That looks like that would be the derivative of my original problem. Now, see here. See. Now, some of you might be thinking, I'm going to give you some more examples. Some of you might be thinking, wait a minute, why didn't you just take this 1 that's on this power and bring it down? You can't just, anywhere you see an x, do the power rule. Okay? You've got, the function has to be x raised to a power. That's not what this is. The x is in the bottom. So we had to rewrite it like this first before we could ever use the power rule. Okay? So that's why I did that. All right, now we write it like this. And we were doing the derivative at 4. So now put a 4 in for x. 4 squared is 16. Negative 2/16.
See what we could have done.
See what we could have done. Well, I told you it was a long way and they can get a shortcut. I know.
I feel like throwing some.
Okay? But the good news is we don't have to do the long way very much. And a few more times, practice it on a quiz. Most of the year, we'll be doing that. Doing the power rule, finding our slope. You can see why then we wouldn't have to do that. We wouldn't have to get on a calculator and then plug in the 4 and see what the slope is, because that power rule is pretty fast. When you get good at it, it's really fast. And you can put a 4 in and you can find that derivative or that slope a lot faster than even going to your calculator and putting it in. All right. Now, let's practice some. In your notes, you might want to make, I just made a little chart here. And we're just, on the left side is f, and on the right side, we're going to write down some f primes. Because we've just learned this power rule. And we already know about sine and its derivative. But we don't always get functions that are x squared and x cubed and stuff like that. We get them shifted and stretched and compressed. Right? So how does that affect the derivative? Well, let's think of it as graphs. Let's think about how it affects the slopes. Okay? How do these shifting and stretchings affect the slope? And that's how it will affect the derivative. So let's take this first one. It's an x to the 5th. Now we know normally the derivative, we bring the 5 down in front, we drop it to a 4. That's how you do the derivative. But we've shifted this where? 4 to the right. So will that change any of the slopes on the curve? It won't change them at all when you shift it to the right. Slopes will all be the same shape graph. But where will the slopes be? Shifted 4 to the right. All those slopes on the regular x to the 5th graph are now going to be shifted 4 to the right. So the derivative is going to be shifted as well. So it turns out that the derivative is a 5 brought down in front. The inside stays exactly the same. And we drop the power to a 4. Now you're going to hear me repeat that over and over again, but the inside stays the same. It turns out all the time on these functions, if we've got stuff on the inside, that same stuff stays on the inside when you do the derivative. It's just a rule that we will see over and over again. All right, so let's do this next one. You got a 3 multiplied on the inside. What does that do to the graph?
Horizontal shrink.
Horizontal shrink. When the number's bigger than 1 on the inside, it's opposite of what you think. It's a shrink. So let's take a graph and shrink it by a 3 factor. Now I think it changes 2 things. First of all, it changes where all those slopes happen, right? Because they're now all pushed in by a 3 factor. So not only is the F graph been shrunk in by 3, but the slopes have been shrunk in by 3. Well, the inside stays the same. That's what I said. So the derivative is going to keep a 3 on the inside. But what else has happened to the slope? They're all bigger. Because when you compress that graph, it's now 3 times as steep as it was before. When you used to run and go up this much, now that you've compressed it, if you run that much, you're going to go up 3 times as much. So we have to multiply the slope by a 3 as well to account for that. So here's what's going to happen. You're going to have your normal power rule. The 6 will come down front. The inside stays the same because that's the shrink. So all the slopes are going to be compressed and happen in, okay, at their new location. And we're going to have to kick out and multiply by a 3 because all the slopes are going to be 3 times as much. Right? When you do that compression. All right. And then we would normally simplify that. And we'd write 18. And then we'd put 3x to the 5th like that. There's going to be some in your homework where this is what you do. Matter of fact, there's only 2 I'm going to give you. You have to do the long way. And every other problem in your homework that says find f prime, you're going to do this shortcut. Okay? All right, so what about sine 2x? What's that 2 do? Another shrink. So what that means is we know the normal derivative is what? Cosine. But we're going to keep the 2x in there. The inside stays the same because all those slopes are going to be at new locations shrunk in by a 2 factor. But what else is going to happen? They're going to be twice as steep because you've compressed them. So the graph goes up and down quicker. So we're going to have to kick a 2 out. I usually put it in front. So we're going to have to kick a 2 out in front. All the slopes will be twice as much. So we have to multiply by a 2. Okay? What about this one? You got a 3 on the outside. This is what we were talking about before. I said, what happens if a number is stuck on the outside? What's that do to the graph? Vertical stretch. Now, does that change where the slopes happen? No. But all the slopes are going to be what? Multiply by 3. So we're going to have to multiply. So normally the derivative would be cosine. Derivative of sine would be cosine. But that stretch is going to make all the slopes 3 times as much. So that's why we say if you multiply on the outside by a number, it just stays there. It just stays there and you just do your normal derivative. Because it's a vertical stretch and that's going to also change the slopes by that same amount. Okay? What about 7x? Well, first of all, that's just a line. And derivative means slope. So what's the slope of a line 7x? 7. So it's got to be 7. What about our new rule? Does it fit our new rule? Well, our new rule, we just said if you have a 7 on the outside, it just hangs out there like the 3 did. And then we'd have a 1 right here, right? So you'd bring the 1 down in front. 1 times 7 is 7.
Get excited.
No, when you bring the 1 down in front, it does not turn into a 17. Okay? Thank you. I hope you wouldn't do that. Bring the 1 down in front. 1 times 7 is 7. And then the power changes to a 0, which x of 0 is just 1. So, yes, it would be 7. Okay, what about the derivative of 5? What's the graph of 5 look like? A horizontal line. What's the slope of a horizontal line? 0. Does that fit our new rule? Well, actually it does because there's an invisible, I'll put some red dots on it so you can see it, but it's really invisible. These are magic red dots. Okay, 5 is the same as 5x to the 0, right? So now do the power rule. You bring the 0 down in front, bring the 0 down in front, and of course 0 times 5, that's going to wipe out everything. So it's just going to be 0. So it fits the power rule, but what you want to think of is, hey, it's just a constant. The derivative of a constant is 0. Okay? Let's look at a few more. We just did those. Okay, let's try a few of these. Okay, 1 over x cubed. Now the temptation is to just look at that x cubed in the bottom and turn it into 3x squared. And you can't do that. Okay, you can't just take an x wherever it is and just do the power rule. It's got to be x to a power. So we first write 1 over x cubed as, we have to first write it as x to the negative 3. Okay, then we can do the power rule. So the derivative would be x to the negative 4th, right? Now, if we wanted to, we could then write that as negative 3 over x to the 4th, but there'd be no usually rearranging stuff is not important to me as far as simplifying. I don't, unless you need it to go on later in the problem, then you might do it. But just rearranging where that x is, up, down, whatever, I don't care. So if you leave your answer like this, I'd say that's fine. But we can tell that the answer definitely, we can tell we should not have just made that 3x squared down there, because that definitely did not give us the right answer. Okay? So this is what we want. All right, what about square root of x? We first make that x to the 1/2. So we're going to get into fractional powers. This works. X raised to a numeric power gives you this. So that would be 1/2 x to the negative 1/2, right? If you take 1/2, subtract 1, that's negative 1/2. So we're going to have to be able to do some fraction adding and subtracting in our heads probably without a calculator. Okay, not terrible fractions, but just do it this. 1/2 take away 1, that's just 1/2 take away 2/2, right? Do it that way. All right, this we would rewrite as x to the 4/3. That's right. The root goes on the bottom. The root goes on the bottom. So now its derivative would be 4/3 x to the 1/3. 4/3 minus 3/3 would be 1/3. Okay? So it works with negatives. It works with fractions. All right? What about the next one? We have a sum of individual terms. 3x to the 4th minus 2x to the 3rd plus 8. Well, what's your best guess at what the derivative would be? What do you think? Would that be reasonable? That would sure be nice if it works that way, and it turns out it does. It turns out it does. If you have a sum or difference of individual terms, you can do the derivative of each individual term. So the derivative of this function is 12x to the 3rd minus 6x to the 2nd plus 0. Sorry. You don't have to put the 0, obviously. What did we say the derivative of a constant is? 0. Derivative of 8, 8 is just a horizontal line. 0. Think of it this way. Think of it like a vertical shift. Think of that plus 8 or plus 7 or whatever's on the end. All that does is vertically shift. Does that change the slopes? Change where they're at? No. Remember how we said one f prime graph could have an infinite number of f graphs? Okay? Here. What's the derivative of x cubed plus 2? What's the derivative of x cubed plus 2? 3x squared. What's the derivative of x cubed minus 7? 3x squared. What's the derivative of x cubed plus 9? Remember how we said that when we were doing graphs? One f prime graph could have an infinite number of f graphs. They would just be vertical shifts of one another. That's because when we do the derivative of that constant, it just goes to 0. It just falls away. Okay, so different f graphs all have the same f prime graph. All right, this last one. Now, There's a connection here to what we just did. We had a sum of individual pieces. We said it was okay to do the derivative of each piece. Is it going to be okay to just do the derivative of each individual piece? I mean, it'd be nice if you could, because it was sure nice here. That was easy. We just did each individual piece, and that was our derivative. Well, there's a way to check on this one. What do we know x to the third times x to the fourth is? We know that's x to the seventh, has to be. And according to our power rule, what's the derivative of x to the seventh? Has to be 7x to the sixth. Is that what we'd get right here? No, we would get 12x to the fifth. So it turns out that it's nice for sum and difference. If we have a sum of individual terms, we can do each individual derivative. That's nice. If we have a product of individual terms, we can't do their individual derivatives. It doesn't work. So if we had to do the derivative of this, and if I'd have given this one to you a minute ago, probably should have given you this one first, I'm guessing the vast majority of you would have said this. Right? That would sure be nice if that happened. Turns out it doesn't. So, stay tuned to chapter 3. We'll learn how to do that.
You can't
Or,
just, I really wanna look
okay,
that up,
if
but
you-
I can't.
if
do
you
it.
just can't wait,
I just want to know what the
if you just can't wait, get your calculators out. Surely the calculators will do it, right? This is what the calculator, this is why we got the cast version and not the non-cast version. The cast version will actually do these derivatives. This will come in handy at various times. Now, you will be given a quiz, and there'll be multiple times where you have to know these derivatives on a no calculator thing. But there will be times where we'll be really glad we can just do a derivative right on our calculator. So if we go to the scratch pad, now, I'm going to show you where this is. I'm not even sure why, because you'll never use it. But if you're on the calculator, if you went to menu, calculus, and right there, number 1 is derivative. But here's where you'll usually go when you're on the calculator screen, right next to the 9. That's the template button. It's got a bunch of different templates like square roots and stuff like that. When you push that button next to the 9 and you go right over here, the one that's highlighted up here on the screen, that is the derivative template. Notice it uses the Leibniz notation. Okay? So let's say we wanted to do the derivative of x cubed. What would we put down here in the bottom? We'd put an x, because that's what we're doing with respect to. If we want to do t cubed, we'd put a t there. Okay? And then inside this box, we put x cubed. And so this will be the derivative of x cubed, and we hit enter, and there it is. You want to do the derivative of sine, okay, with respect to x, hit the trig button, sine x, derivative of sine is cosine. And so, if you really want to, you can type in that one we just had up on the board and see what the actual derivative is.
cube times sine
It was x cubed times sine of x. And you can see it is not just the individual derivative.
of. Oh yeah, I can see that.
Yep. Now you might see a pattern there, maybe not. But anyway, we'll deal with that later on. All right.
I guess.
So, if you want, now listen, if you want to use your calculator as a tool to help you with a few things on the homework, you can, but I would try to do whatever you can without it, like do the shortcuts, maybe check them up here. The calculator's not always going to write them the same way you would. Now remember the one we had where we said, let's say the derivative, let's do that one real quick, the derivative of x to the negative 1. Okay? Or what did we have? Let's do that one. X raised to the negative 1. Now we wrote it negative x to the negative 2, right? Negative 1 x to the negative 2. But you can see that's the same thing. So the calculator doesn't always write it the same way you wrote it. It tries to simplify. Now remember problem number 44 that we did today? and we had to do the common denominator thing, calculator will do all that for you. You're going to have a quiz where you have to do it, though. You have to do that algebra. But so you can check at least. So what did we have there? We had a, remind me, it was 2 divided by 4 plus h.
Yep.
Is that right? And then it was minus 1/2. And then it was all of that divided by h. And I can type that in, and it'll just do all that algebra. And that's what the that's what the CAS part does. Okay? And remember, that's what we had, right? We put a 0 in for h, we got -1/8, that's what we had. So, I mean, if you just really get stuck, or you want to see, you know, what it should have been, or whatever, you can put some of this algebra stuff in, your calculator will do it. All right. For your homework. All right, we're going to do this line here. And this line that's right below it where it says do the derivative. So we're doing by the definition. So we're doing these two things right here. All right? So most of these are kind of shortcut kind of things. So, all right, if they want to find f prime of 1, think about where we started today. Think about the question I opened the day with. We just found a new one. Okay, we started the day with this question right here. We just found a new one. You want to find f prime of 1? First find f prime of x. What would f prime of x be here? 2x minus, no, 1x is just a line, right? Just 1. You'd have a 1 here. You bring a 1 down in front, drop that to x to the 0. X to the 0 just 1. It'd be 2x minus 1. If that's f prime of x, then what's f prime of 1? Right? That's what it'd be. If you want to find f prime of 1, you're going to hear me say this a lot this year. If you want to find f prime of 1, first find f prime of x. And now we know how. We know a shortcut for doing it. So you want to find f prime of 1, let's find f prime of x. Do our power rule. It's that. Now plug in a 1. Slope is 1. So there's add another way to our list of ways to do these things. Okay? So a lot of the homework questions will be that kind of thing where you're going to get to use the shortcut. The only two that you have to do the long way are these two. 1 over x and square root of x by the definition. Now, that's going to let you practice those other two algebra things that I said you're going to need to be able to do. 1 over x, that's a lot like number 44. Remember, 44 was 2 over x. So if you want to refer to something, doing the derivative of 1 over x is going to be just like number 44 was, very similar. Except you won't be plugging a 4 in, you'll just be plugging x in. Okay? And we already know what that derivative should be by the shortcut. So you'll be able to check your answer. And this one's going to let you practice that conjugate thing with the square root. And again, we know square root of x is x to the 1/2, so by our shortcut, we know what we should end up with, and we'll be able to check that. Okay, so those two are the long way. Everything else in the book that you're doing, you can do the shortcut. All right, you can go ahead and get started on those.